Velocity time graph example part 2. In the previous tutorial, we have explained the example in figure 1.1.8. Let's continue with it. Here we can say that where a velocity time graph is a straight line, like here in the first part of the graph, or in the second part, if we call these points A, B, and C, from O to A and from B to C, we can say that the acceleration is uniform. Acceleration may be represented as the rate of change of velocity with time. The graph in figure 1.1.8 also gives information about the distance traveled. Between 4 seconds and 9 seconds, the object traveled with a uniform or constant velocity of 8 meters per second. Here the time is equal to 9 minus 4, which is equal 5 seconds. So during these 5 seconds, the object has a constant velocity that is equal to 8 meters per second. We can use these information to work out how far it traveled, or as we call it, its change in displacement. So we have the equation velocity equal change in displacement over time taken. If we rearrange the equation, we have displacement equal velocity times time taken, which is equal to 8 times 5, and the final answer is 40 meters. Or we can get the change in displacement by getting the area of the rectangle, that is area equals length times width. From the graph, L equals 8 and W equals 5, which gives us the same answer, that is 40 meters. If you look carefully, you will see that this change in displacement represents the shaded area under the flat part of the graph, because the area under the graph is calculated by multiplying together a velocity and a time. Meter per second times second, which is equal to meter. The answer is in meters and so represents a displacement. In the same way, the area under other parts of the graph represents displacement too. For example, like this shaded area in green, here we can get the displacement from O to A by getting the area of this triangle, which is equal to height times base over 2. So the change in displacement during initial acceleration equals 8 times 4 over 2, which is equal to 16 meters. And if we get the area of the triangle shaded in pink, we have the base equal 8 seconds and the height is equal to 8 also. So the change in displacement during the final acceleration equals 8 times 8 over 2, which is equal to 32 meters. Here the height is in meter per second and the base is in seconds. That's why we get the answer in meters. Now if we want to get the total displacement, all we have to do is add up all the displacement that the object has taken at each part. The first part is 60 meters, the second part is 40 meters, and the third part is 32 meters. If we add them up, we get 88 meters. And these are the most important information that we can get from velocity time graphs.